Welcome everyone, my name is Owen Reeves. I'm an associate professor at the University of Bergen, and this is your lecture on seafloor hydrothermal systems. What you are looking at is a black smoker vent at a place called Aurora, which is located 4 kilometers deep at the bottom of the Arctic Ocean under sea ice. This is a black smoker vent, which is part of a seafloor hydrothermal system, and we're going to learn about exactly what goes into that system, what happens underneath what you see here, and what produces this spectacular venting that we see. We'll do that through the slides that you're about to see, the papers that I'll be assigning, and the activity. So welcome along. Okay, so in this lecture, we will get an introduction to the geochemistry of seafloor hydrothermal systems. To create a seafloor hydrothermal system, or any hydrothermal system, hydro, water, thermal, heat, you need 3 things. You need a heat source, you need some sort of permeable medium, and you need water. If you have those 3 things, you have a hydrothermal system. And one of the reasons we knew hydrothermal systems existed, they were discovered in the late 70s, when we actually saw them for the first time. But in the 60s and 70s, we knew they existed because of what we call the heat flow anomaly, or the missing heat. We knew that at the global mid-ocean ridge system, the observed flux of heat was actually lower than what you would predict would be coming out of new ocean crust that was being generated. So why was there missing heat? Well, what they were measuring was what we call conductive heat flow. If you touch a hot surface, you know what conductive heat flow is. And what was missing was actually convective heat flow. And the convection, the boiling of water in a pot of pasta, is convection. And that difference, what we call the heat flow anomaly, was actually really greatest around the mid-ocean ridges. And they knew this missing heat must be going away through a convective process. And they actually even knew that about 3 terawatts in terms of heat was coming out at the axis, and a lot more was coming out off axis. And they even were able to understand that as the crust ages, when you move away from the mid-ocean ridge, at about 65 million years roughly, there's no more circulation anymore. And this is quite far from the mid-ocean ridge that the observed heat flow and the predicted start to line up again. So there you don't have any missing heat anymore. So here you see the idea of a hydrothermal system. You have a recharge zone where water is going in. There's a deeper part of the system that's often called the reaction zone. We call it the root zone, the deepest part of the system. And then there's an upflow or discharge zone, which ultimately leads us to those smokers that you saw in the introduction. Hydrothermal systems as a whole are a global phenomenon. They are everywhere, and this is one of the more recent maps showing where they are. All these red dots are confirmed sites, yellow dots are suspected sites. This map is changing every year. There's a lot of missing space in the Southern Ocean. Don't let that fool you. There are hydrothermal vents there. We just haven't found scientists or ships brave enough to be in what we call the roaring 40s and the furious 50s. It's a very, very difficult place to go to sea down here, and you need a strong stomach. You see most of the vents are located around the equator, where it's quite nice and pleasant. Aurora, the system that I just showed you, is this red dot way up here in the Arctic. Okay. So the type of heat source you have depends really on what kind of setting you are in the mid-ocean ridge, what the heat source that is driving your hydrothermal system. And it varies with the spreading rate, and this also has an effect on the fluids. If you are in a fast-spreading environment, like in the East Pacific Rise, you have a very clear axial magma chamber. So it's much like a linear volcano. It's very easy to find these magma chambers, and they come up quite near the surface. But when you get to slower spreading rates, even ultra slow spreading rates like we have here in the Arctic environment, it becomes much more complicated. What's happening there is you have not only volcanic You have magma coming in, but you have tectonic processes coming in as well. And this is ultimately what's helping to create the permeability to drive your hydrothermal system. You're pulling plates apart, you're cracking open crust in both fast and slow, and it happens very fast in the fast spreading, and it happens quite slow in the slow spreading environments. And in these tectonic systems, where the things are very, very slow, very large faults are ultimately what's controlling your access to heat and where the seawater can go in. Now, in these ultra slow spreading Arctic mid-ocean ridge, we have a variety of different vent systems that occur at a variety of different conditions. Some of them are very, very shallow, only 100 or 200 meters deep. Some of them are very, very deep at several kilometers, and this has an effect on the vent temperature, which you see here. The deeper systems tend to be hotter, and the shallower systems tend to be much lower in temperature, and we'll talk about why that is as I go on. So let's take a journey now. If we start with seawater and we go into this recharge zone that I mentioned previously and think about the composition of seawater, what it's made of, which I've listed across the top here. The dominant things in seawater are sodium and chloride. This is what we taste when we go swimming. The next most abundant thing is magnesium, then sulfate, and then lesser elements as we go on. And these all change. So these go into our hydrothermal system. Reactions happen. One of the reasons actually we call the root zone is because reactions are happening continuously through the system, not just in the deepest part. So some people likes to call that the reaction zone, but it's a bit confusing. So let's just start. We've gone into the crust now. We're starting to heat our seawater. Up to about 40 degrees, you're essentially going to consume the oxygen in seawater. There's a lot of iron in basaltic crust, and so that's essentially going to create a lot of iron oxyhydroxide, or rust to you and I. You're also going to start to remove some of the sulfur that's in your basalt as sulfide and create a little bit of sulfate. So you've already become anoxic now. Your fluid has lost what little oxygen it had. You start to take up some of the elements in the alkali group. They start to be absorbed as you go further on. And then you do things that actually also happen in cold ocean crust, what we call seafloor weathering. So you can start to lose a little bit of magnesium, calcium, and silica. Many of these reactions are a little bit confusing because they will change direction now as we go up in temperature. So let's continue on. We're still in the recharge zone, but we're going up in temperature now. Above 150, things really start to happen. So our magnesium here, which is our third most abundant element in seawater, this gets almost completely removed from seawater to form magnesium silicate minerals. But look on the right side here, what we are getting in this reaction, 2 protons. Now, if we think about that, there's about 50 millimoles of magnesium in seawater. If you will remove all of that on the left, you will create 100 millimoles of protons. That is an enormous amount of acidity. That would give you a fluid of pH about 1. Most black smokers are pH around 4. So we see that not only can this create a lot of acidity, but a lot of that acidity has been consumed, and this is ultimately what alters the ocean crust, is this extreme acidity that you generate. Below 200 degrees, you're forming something like smectite. Above 200 degrees, something like chlorite. The next critical thing that happens is the precipitation of calcium and sulfate from seawater as anhydrite. Anhydrite is a funny mineral that has what we call retrograde solubility. It precipitates at higher temperatures. And there's a little bit of an imbalance here. We have about 28 millimoles of sulfate in seawater and only 10 of calcium. So you take about a third of that sulfate away when you precipitate it with the calcium. But we will get more calcium as we go along. I'm about to show you in a second. Ultimately, we're going to remove all of our sulfate just like we remove all of our magnesium. Now, we don't really know what the recharge zone looks like. We've never found one. It's obviously very difficult to see where seawater goes into the ocean crust. It's not obvious. So how we study the recharge zone is actually through the rock record. And this is an example from a beautiful site that the ocean drilling program drilled in quite old ocean crust that had moved away from the mid-ocean ridge boundary. And you see all of these minerals. You see the iron oxyhydroxides. You see your chloride and smectite. Here's our anhydrite here showing up all the way down. And this is essentially recording fluids that have long since gone, but they have left their record in the rock sample you see here, where you see all that oxyhydroxide and you see the precipitation of things like anhydrite in the vein spaces. So let's continue on. Now we're getting really hot. We're going to hit the root zone. This is usually where the heat source is, the magma chamber or very, very hot rock. What actually happens here is much of the final chemistry is kind of decided in this root zone. We start to remove a little bit of sodium, replace it with calcium. This is great because this helps precipitate the last of our sulfate that we had left over. And I said this fluid is very, very acidic. This is really when you start to dissolve iron, manganese, and other trace elements from the original crust, from fresh rock. They become very, very soluble. And we can see this. We actually know this from hydrothermal experiments. And you can see as a function of temperature, iron and manganese are very, very sensitive to what temperature you react your basalt at. So at 400 degrees C, you can get a lot of both in solution. But you go down to 350 and 300, the fluid can't really carry so much anymore. So it's a very, very sensitive indication of that. Let's continue on. What else is happening here? The fluid is finally getting its composition governed by the situation that it's in. We start to basically react water, which generates a little bit of hydrogen. And the mineral assemblages that are present in our altered rock and in the fresh rock during that whole alteration process, that's ultimately what will now buffer or regulate the redox state of the fluid. So how oxidizing or reducing it is. That's ultimately going to be governed by these minerals. And this is a typical diagram that people like to show. The mineral assemblage, or the group of minerals, pyrite, pyrrhotite, magnetite, and hematite, this pretty much is the gang of guys that will regulate our system. Ultimately, the hydrogen is actually coming from splitting water by this reaction that we see here. One thing that can happen when you're in the deepest and hottest part of the system, and also as you come up, is seawater at that point, it's going to boil at several hundred degrees. So if you hit what we call the two-phase boundary, where seawater will split into a liquid and a vapor, you will do what we call phase separation. And this happens the vast majority of hydrothermal fluids. It was debated back 40 years ago, could they do this? And then it was finally proven that yes, they definitely do this. And this is what we call below a certain temperature, called the critical temperature boiling, like you boil a pot of water at 100 degrees in your kitchen. But if you go to 3-4 kilometers depth, where you have 300 or 400 bars, 300 or 400 times the pressure in your kitchen, you're going to boil at 300 or 400 degrees. What happens there is you create a liquid phase and a vapor phase. And you can actually see this in some smokers. They kind of look like they're flashing. And it's a trick that we use when we're on the seafloor to see that they're actually boiling. When it's hotter than this magical temperature called the critical temperature, very, very funny things happen. You create very highly concentrated salty fluid and a lot of vapor. And how this affects the fluid chemistry is essentially all of your ions, they like to stay in the liquid, and all of your gases like to stay in the more gas-like vapor. And so you start to split your chemistry apart, and then the fluids that we measure at the seafloor essentially records different amounts of vapor and brine. Sometimes it's pure, sometimes it's a mixture. It's the biggest driver of salinity effects. Now, this is happening anywhere from the root zone all the way up through the upflow zone. And the upflow zone, we don't really think that very many reactions happen in the deeper part of the upflow zone. Why is that? Well, the fluid is so buoyant, it is coming out of here at an incredibly fast rate. We don't really know how long a fluid stays in a seafloor hydrothermal system. We think it's probably years, but this is an active area of research from the time it goes in, heats up, reacts, and come out. But we know that this last part is incredibly fast. We're talking minutes, maximum hours, definitely not days. So not too much goes on in the upflow zone, but when it gets closer to the seafloor, which is a very cracked and permeable place, you can start to have mixing. Seawater is going to get in there, it's going to mix with your fluid. A bunch of things will start to happen. You have dissolved a lot of metal, a lot of hydrogen sulfide, and you're in a very acidic fluid. And of course, when you come to seawater, which is alkaline, your chemistry situation is going to completely change. And then at the seafloor, you will start to deposit what we call massive sulfide. Iron sulfides, other metal sulfides. This is a natural acid-base process that you will learn about in the references. So what happens then is you start to make spectacular structures. These are the black smoker chimneys that many of you have probably heard about. They vary in size and style substantially. So you can have ones that are little ones, smaller than your hand, up to tens of meters high. The biggest one that we ever saw was about 45 meters high. This was called Godzilla. Here's the Alvin submarine for reference. This was an enormous structure. I think it collapsed a few years ago. But depending on the fluid chemistry and how the fluid is coming out, it will build completely different spectacular structures. It's always fun to see. How does it actually build the chimney, or how does it start? Well, we have a model for that. The first thing that happens when seawater is exiting the seafloor is you have your 350 degree fluid. It will instantly start to precipitate around the hole that it's coming out of, anhydrite, this mineral of calcium and sulfate. We got rid of all our sulfate before it's gone, but now we're back in seawater again, and we have a lot of calcium in our hydrothermal fluid. We have a lot of sulfate in seawater. They meet each other, and they start to make kind of like a scaffolding of a hydrothermal chimney. And what that does is it starts to insulate the fluid inside, keeps the temperature a bit higher and stops it from cooling so rapidly. And then you start to deposit what we call the second stage minerals. These are the higher temperature minerals. Chalcopyrite, this is what we call, when we collect it on the seafloor, bling, because it's nice and shiny. And you can see it here in this figure. Chalcopyrite looks like, it almost looks like gold when you see it. And these minerals are only stable and can only be deposited at very high temperatures. So once the chimney starts to grow, you start to build and build and build and build and build. But the very, very first stage is essentially anhydrite, and then these minerals come later. All that iron that you're carrying in your fluid, once that hits seawater, it's no longer possible for the fluid to carry that iron in a dissolved form anymore. So it essentially precipitates out. What happens is it meets some sulfide, which is also in your fluid, and it starts to make this beautiful black smoke that you see that billows then out into the water column. And actually you can see that. It's a little bit in this figure here, and then you can see it sometimes in video footage. Right at the tip of the chimney, you can see that the fluid is actually clear. And then 1-2 centimeters up, once it starts to mix with seawater, that's when your smoke is actually forming. So seawater is driving the smoke formation process. And essentially this chalcopyrite is, of course, very, very interesting. This is a copper-rich mineral. It's one of the minerals that is essentially driving the explosion in interest in deep sea mining. It's a very copper-dominated mineral. And it's forming at its most abundant form in these chimneys. So as this water, the journey of the hydrothermal fluid doesn't really stop there. These fluids go into the water column. They rise several hundred meters high at a place like Aurora, something like that, several hundred meters. This is actually how we find black smokers. We look for them by looking for this, what we call the hydrothermal plume. It rises up because it's still very, very hot and buoyant, and it's cooling. And when it cools enough, it essentially levels out and becomes what we call non-buoyant and forms a very large crown, kind of like a tree, that spreads many, many kilometers from the original smoker. Within that plume itself, there are a whole host of other processes happening. You are starting to oxidize the metals that made it out. Microbes are living there. They are starting to feast on some of the chemicals in the fluids. These things that are forming then start to react with seawater again. They start to steal elements from seawater, these oxyanions and rare earth elements. They start to get scavenged. It's a process that we talk about. And ultimately, they end up depositing what we call metalliferous sediments. So basically, sediments that are unusually rich in metals. And we can see this when we look at a map of mid-ocean ridge sediments. This is a plot, color-coded, showing iron and manganese plus aluminium divided by aluminium. Now, aluminium is not particularly interesting element in hydrothermal systems, so it's used here as a kind of just a normalizing element. But you can see that the ratio goes way up, here, 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 all the way through the center of the mid-Atlantic. What are we seeing here? We are seeing the global mid-ocean ridge. Very, very close to the East Pacific Rise, we see the iron and manganese deposited from those vents. Also along here, this is the Southeast Indian Ridge, Southwest, and the Central Indian Ridge. It's essentially a map of our mid-ocean ridge system through hydrothermal chemistry.